can prove the intrinsic multidimensional analog of the Jacobi relation, which will be read as follows. Take any random variable x, v, for any v in the vector space capital V. Then xpn is equal to pn plus 1 xp pn plus pn xp pn plus pn minus 1 xp pn. This is the intrinsic formulation. See, it's coordinate free. I didn't do explicitly the Gram-Schmidt orthogonalization. Why? Because it is implicit in the definition of this. Okay? So this is the intrinsic formulation of the three-diagonal Jacobi relation. You see, the non-trivial point is that x, which a priori could have components on infinitely many of these subspaces, in fact, it has components only on 3 subspaces. This is the crucial, very deep part of the Jacobi relation. Okay? Now, from this relation, we have the cap operators, because we have the creator associated to V, we have the preservator associated to V, and we have the annihilator associated to V. Okay? Well, in fact, this is the all, since these are restricted to Pn, this is restricted to Pn. So, this is what we will use in the future. The restriction on this, on Pn, we will denote like this. And then, when you sum everything, you get the cap operator. A epsilon, V will be by definition the sum of all the restrictions. Because when I sum over all n, this becomes the identity. Wait a moment, just a moment. So this will be the definition of the cap operator, and this will be A epsilon V restricted on n, and then the quantum decomposition of the random variable will be as we did in the symmetric quantum decomposition. And molecules. So this is how we arrive to the quantum, because you see, how do you get this? Because the definition epsilon is a plus 0 or minus. Okay, so when you sum this identity, the Jacobi three-diagonal identity over n, this becomes the identity. So you get xp. But this becomes by definition, the sum of all this is A, and the same for the other two. Okay? So we have the quantum decomposition. But now we have a so from now on, now I see you think of a finite dimension, because in infinite dimension, but I try to speak in a neutral language. But you see, in any case, when we consider infinite dimension, we will consider not a topological vector space. We consider a vector space. So the meaning of basis is in the sense of linear space. So any element will be a combination of a finite number of elements of the base. Sometimes this is called in the literature a Hamel basis, okay, in linear algebra. So this is now we fix a basis, and we introduce the corresponding cap operators. And to be quick, instead of writing A, Ej, our basis in this talk will be fixed. So I simply put Aj. Now, what is the, and similarly, instead of writing X, E, J, I will write E, so this is a definition. I will write xj. Now, what is the new point that arises in dimension D, which has no analog in dimension 1? The new point is this, is that the coordinates commute. Remember, these are multiplication operator. I identify any random variable with the multiplication operator by the random variable itself, okay? Of course, if I multiply by random variables, it's commutative. This is an elementary point, okay? Let us see what is the implication. Well, write the quantum decomposition. So let us now, let us do it explicitly and expand the product. So I multiply A by all the other one, and I get A daga J, which get commuted with A daga K, then with the same AJ commuted with A0 K, and commuted with A, this is plus J, commuted with A minus A. Now, do the same for the A0, A0J, A plus K, plus A0J, A0K, plus A0J, A minus K. And the last for A minus, this is are all plus. The last for A minus. So this is A plus, A minus, A0, and A minus, A minus. Now, let us rewrite these objects in a more intuitive way that will give you more insight. So, let us rewrite them in order of what is their range. Look, this is a daga is a daga J, a daga K, minus a daga K, a daga J. But since any A daga increases the gradation by 1, if I apply to n, this will be increased by 2. So this is the highest order term. Then there will be the terms that increase the gradation by 1. Which are these terms? They must contain at least one creator, exactly one creator. So this one increases because this gradation preserving, and this increases by 1. Okay, so I have A daga J, A0 K, but there is another one because also this is only one creator. Okay, so there is no, sorry, this is minus. This is only one creator. One is preserving and the other minus. I need one plus. So plus is here and the plus is here. So this is J0K and this is 0JK. This is the correct. So this increased by 1, and it seems to me there is nothing. And the most interesting is the one that gradation preserving. So it must have degree 0. The degree 0 I obtain either because there is a plus minus or because there is 0. So where there is plus minus is here, A plus, J, A minus, K, plus. Then here there is 0, 0, so A0J, A0K, and here there is minus plus. So I have 3 terms in this commutation relation. Now there are other. There is the one that decreases 1. The one that decreases 1 must have a 0 and a minus, because you want minus 1 the degree. So 0 minus, where it is here. It is here, A0J, A minus K, and it is here, A0K, A minus J. And there is the last one, which is degree minus 2, which is A minus A minus. Now, I have written in such a way that in each row I go in a space of orthogonal polynomial of different degrees. And we know that these spaces are orthogonal, not only being in Hilbert space, they are also the harmonic polynomial. So they are harmonic of degree n, therefore they are linearly independent. So this goes with values in a space which has 0 intersection with the space where this takes place, where this takes values. And there's 0 intersection with all the other ones. So it means that since this must be equal to 0, the sum of all these terms must be equal to 0, they must be equal separately to 0. That is the crucial point. Because of the linear independence of the spaces of the gradation, from the fact that the sum of the operator is 0, each of them must be 0. So we get what is the main point, the main new point of the theory of multidimensional orthogonal polynomial, and also in quantum mechanics is very new, this idea. This didn't exist. And which are the commutations? So now last remark, we have 5 rows here, but you see, if I take the adjoint of this, I have the adjoint of this will give the adjoint in reverse order. So this will give minus this. So if this is 0, this if and only if this is 0, if and only if this is 0. Similarly, so if I for this, if I take the adjoint of this, I will find this. Okay? The adjoint of this will give me this, with the J and K exchanged. Okay? So this is equivalent to this. So in fact, I have not 5. The independent commutation relation are only 3. And precisely that. This is very nice. This is very important. The creators commute. This is a fact that was very well known in the quantum mechanics in bosonic case, but now we know it's true for all polynomials, for all quantum theories associated to orthogonal polynomials. And these are the 2 new commutation relations. This one when A0 is 0, symmetric case, I will show that also in multidimension, the theorem that characterizes symmetric random variable in terms of the preservation operator. So preservation operator for a symmetric classical random variable is 0, and conversely, if the preservation is 0, the random variable x is the random field is symmetric. So in the symmetric case, you find something strange, which is I write in general then.
Sir, is this like you said about the bottom lines?
You have started some.
So second and third last equations.
This is first, second, and third.
No, it will be from the bottom. Yeah, that is the second and the third is.
Ah, sorry. You are right. I am copying probably the wrong thing. So, sorry. You are right. I am copying the thing. This is the second. This is the second. And this is correct. This is now this one. And this is correct.
So these two of the same type.
No. Let me copy. This is the new commutation relation. Okay, so now so you have two types of commutation relation. This is a typical for multi-dimension, because you see that whenever I put a j equal to k, all these relations become trivial. That is why in one dimension they did not appear. Okay, so they become trivial in one dimension. But if you remember what we did, in one dimension, of course we didn't use this because they are all trivial. They are all 0 equal to 0. But in one dimension, we deduced the commutation relation. From where? We deduced it from the orthogonal gradation. So there are now, and this we can deduce also here. So from the fact that so you see, take all possible combination, plus minus, plus not only of this form, so the preserving combinations. So these commutators preserve gradation. So I can repeat for them, and I can the same argument that we did in one dimension, And so we can say that the operator A dagger J, A minus. In fact, we can do even more, because if you remember, I insisted on the fact that in one dimension we have much more than the commutation relation. We have the multiplication table. So we, instead of considering commutators, we just consider products, which are gradation preserving products. The gradation preserving products are only three: plus minus, minus plus, and 0, 0. Okay? So these operators are certain operators. So this, let us begin with the most important, which is this one. This one will play a very important role in the future. So if you remember, this was called omega lambda. In fact, this was omega lambda plus 1. We will call this omega tilde, jk. So this will map any space of the gradation into itself. See, now life is no longer simple, because when we were in dimension 1, each Pn was one-dimensional, because there exists only one monomial of degree n. But now we have that this is the space of orthogonal polynomial of degree n, whose dimension is of order n to the power d minus 1. So you see that these are, it's true that they are square matrices, but they are square matrices of order which increases like a power.